Let's start this session. First thing, for those of you who haven't noticed, today is a quiz 3 all day. Some of you have taken it already. The rest of you have until midnight. Once you log in, you'll have 15 minutes to finish it. And on the subject of tests, a week from today, next Wednesday, the 24th, we'll have our first full hour test. So that will cover everything that we've had up through today. It will not cover the class period on Monday, but it will include chemistry for biology, which is what we're doing today. So any question about that, the quiz today or the test next week?
Yes, I've got a question. So today's test is on the stuff we reviewed last week.
Yes, yeah, that's right. Today's test is, well, it's actually on 3 topics: the structure of life, life in the universe, and classification of organisms. I remind you that I want to encourage participation. That's how you get credit for being in class, and you also get extra credit towards your final grade if you participate. And you'll have to tell me your last name when you speak so that I know it's you.
Professor?
Yeah.
Last name, what are you in? So for today, it is the quiz or exam?
Today is a quiz. Next Wednesday will be a full hour test. Oh, and I should emphasize that there will be no class next Wednesday. So the full hour that you commit to this course, you'll use on the test, and you won't show up for class. You have all day to take the test. It's just like a quiz. When you log in, you'll have 75 minutes to finish. But you can do that anytime between midnight and midnight next week, next Wednesday.
How many questions is it?
Oh, I don't know. It doesn't really matter. It is more a question of what kind of questions are they and what do they ask you to do. But it'll be very much the same as the quizzes you've had so far. Same type of questions at about the same level.
I have another question. So for the quiz for today, is that gonna be like some sort of writing or like answer the question through writing?
There's one question that takes a tiny bit of writing, but only a few words.
Okay, thank you.
Okay, anything else? Today we're going to deal with chemistry, and that's chapter 2 in your textbook, pages 27 to 54. And you may have noticed that I sent you an assignment on chemistry, which is worth 35 points, so it's worth doing. And that's due next Monday. So, and that will be graded.
Okay, I do have one question on that. I saw the format that it's in. Do we print that in and then, or print that out, fill it out, and then resend it? Or
Yeah, I think the easiest way for you to handle it is to download it to your hard drive, fill it out, then upload it back into Canvas, and then it comes to me.
Cool.
Basic chemistry for biology. Everybody see that? Should
Yes.
be eating up 100% of your screen.
Yes.
So why do biologists need to understand chemistry? Well, it's because all life is composed of matter. Matter occupies space and has mass. And living things are really chemical reactions. Thousands and thousands of chemical reactions, all running simultaneously. And each one of these involves a reactant or reactants, which yield products. A plus B goes to C. So biology really is, at its essence, chemistry. We start with atoms, smallest components that an element can be broken into by ordinary chemical means while still retaining the properties of the original element. So we're made of the same stuff that's found throughout the universe. When the universe began with the Big Bang, almost in the entire result of that was hydrogen atoms. But with time, hydrogen atoms started to fuse into helium atoms, which eventually fused into heavier elements such as carbon and oxygen. And these elements were released throughout the universe. And some of them reached planet Earth. And that's how life began on this planet, probably in the primordial ocean. So the same materials that are distributed throughout the universe are the ones that we find here and that we as living things are actually made of. A material that's made of only one type of atom is an element. Certain elements are represented in living things abundantly. The most prominent are carbon, hydrogen, nitrogen, and oxygen. But there are others. These are usually represented by a single letter, and some of them by two letters, like magnesium and iron. All of these elements are organized into a chart called a periodic table, based on the relatedness of elements to each other. There are 94 naturally occurring elements. About 25 of these are essential for life. There are 4 that you need to remember for sure: carbon, hydrogen, oxygen, and nitrogen. I remember them as Chan. And you'll see that in the periodic table, 3 of them, elements 14, 15, and 16, are together in the table, and hydrogen is off by itself. Now, each little box on the periodic table has information in it, quite a lot of information, and we're going to go over that. First, the atomic name. Atomic name in this case is cobalt. The chemical symbol is CO. The atomic number, 27. Atomic weight, 59, 58.9, rounded out to 59. And the electronic configuration off to the right here, which we'll talk about later. Again, the main elements found in life, their symbols and their atomic numbers. These elements make up about 95% of the mass of any organism, any living thing. It's about 95% these elements. There are some minor ones to see here. And you see their symbols and their atomic numbers. Compared to the major ones, these make up less than 1% of the total mass of a living thing. And then there are trace elements, which are almost negligible, but not really, because they're essential. Most of them are essential for life. In fact, they all are, but they're less than 0.01% of the total mass. Well, why do we need these? Well, there are some specific examples like calcium for your bones, magnesium. When we talk about enzymes, you'll find that as a cofactor, many enzymes need magnesium in order to be functional. Iron helps us carry oxygen in blood. Sulfur is a component of 2 amino acids, and they are essential for chemical bond formation. Copper and hemoglobin and potassium, nerve conductance. Now, how do we get elements into our bodies? Well, we eat them. And we can take supplements if we have a deficiency in our diet. And so, for example, a deficiency can result from disease. For example, we'll talk about cystic fibrosis later. And that disease causes problems in absorbing nutrients. So patients often have to take additional supplements, such as what you see here in this label for a complete vitamin supplement. You'll often find over the counter in pharmacies. Atoms are composed of what 3 particles?
Protons.
Just a minute. I want to show you something, and I'll see if you appreciate it.
I can give you the basics of the atom in 2 minutes. You'll understand it perfectly and remember it for months.
2 minutes? You're crazy, you know that?
I can teach you about the atom in 2 minutes. Will you go back to school and finish out the year? How about it, huh? Come on, you're a betting man. How about it, Arnold?
Yeah. Yeah, okay, sure, you got it.
I got your word.
Yeah, you got my word. And 2 minutes.
We got a deal.
Yeah, we got a deal.
All right, sit down.
Okay.
There are 3 gangs on the street, right?
Yeah, 3 gangs.
And this right here is the territory. Now, here is a neighborhood. Got that?
Yeah.
And right in the middle of this neighborhood is a gang called the New Boys.
Yeah, the New Boys. Good name.
Okay. Out here on the outside of the neighborhood, on the edge of the neighborhood, is another gang. You know, these are real negative dudes, really negative, right?
Right.
Now, they call themselves the elected ones.
All right, the elected.
You got that? Really negative. They don't like nothing.
Right.
Now, they all the time out here circling around the neighborhood, just circling, you know, checking out the New Boys. Now, the New Boys see this, and they get, they figure there's something wrong here, so they make a deal with another gang, a gang of very happy-go-lucky guys. They call themselves the Pros. The Pros. Now, the Pros are very positive cats. See, they got all the good-looking women, right?
Yeah.
Right. See, now the Pros and the elected ones, an interesting thing, they hate each other. So much so that they keep the same number of members in the gang, just in case you did.
Right.
So if I got 10 elected ones, how many Pros do I have?
10.
All right. Now, how many gangs do I have?
3.
Name it.
The New Boys, the elected ones, and the Pros.
All right. Who's here?
The elected ones?
All right. Now, what are they, negative?
Yeah, negative.
All right. Now, who's positive?
The Pros, and you're running out of time.
All right. Now, you see right here, the Pros and the New Boys, they call their hangout the nucleus. Yeah. Now, see, that's a real tough word. It's Latin. I kind of think it's Swahili, and it means center.
Yeah. What is it?
It's nucleus. Say it.
Nucleus. Is that really African?
Say it.
Nucleus.
You got it?
Yeah.
All right. Give you another Swahili word. It's a tron. It means dude.
Yeah. Tron. Dude.
All these gangs like that name so well that they all decide to use it. For instance, the pros right here in the middle start calling themselves the protons. And the new boys, well, they start calling themselves the neutrons. And out here on the edge here, the elected ones, they start calling themselves the elect.
The electrons, the protons, and the neutrons.
Yeah. And all this right here, this is the neighborhood. This is block after block of nothing. You understand block after block of nothing, don't you?
Yeah, I know all about that. And your time is up, Professor BJ.
Good. I was finished anyway. Now you go on back to school, man.
School? Man, all I know about is a bunch of damn gangs that live in a round neighborhood.
Arnold, that's the atom. That's it, man. That's it. What's this right here?
Protons and neutrons.
All right, they call this the what?
Nucleus.
All right, what are these guys up here?
Electrons.
Are they negative or positive?
Negative.
And how do they move?
Round and round.
And if I got two of them, how many protons do I have?
2.
Now, protons negative or positive?
Positive.
All right, and what's all this right here?
Oh, that's the neighborhood.
Which is?
Nothing.
You got it, man. You get an A.
For what it's worth.
That was awesome.
I hope it was at least entertaining. Anybody recognize where that's from? There used to be a TV show called something station WKRP in Cincinnati.
Yep.
I think that's from that show.
Yeah, that was Venus flytrap.
You-
Not to date myself.
Yeah, I'm afraid I've dated myself by showing that. Okay, we'll go back to here. And all right, we'll get on to a more serious approach here. But you just heard about the composition of atoms, protons, neutrons, and electrons. And I like this analogy between an atom and a solar system. In both cases, you have bodies circling around a center point. In the case of an atom, on the left, it's electrons circling around a nucleus. And as they circle, they generate a centrifugal force, which throws them out away from the center. But at the same time, there's this electromagnetic attraction between the electrons and the protons, which draws them toward the center. And it's the balance between those two forces that keeps them a certain distance away from the nucleus. And each of these distances is called an orbit. Similarly, in a solar system, you have a center, the star, or in our case, the sun. You have planets circling around that. And again, it's the momentum of a planet which generates a centrifugal force and throws it out away from the center. But there's a gravitational force between the planet and the star, which draws it toward the star. And again, it's the balance between those two forces that keeps all the planets in our solar system in their orbits. So it's a delicate balance in both cases and very precise.
Professor Taylor.
Uh-huh.
So in this comparison, would the planets then be negatively charged?
Are the planets negatively charged? I don't think that electromagnetism is a factor in keeping planets in their orbits. The two factors are the centrifugal force and gravity.
Got it.
So you don't have those in an atom. Gravity is not a factor, but electromagnetism is. Anybody else have a point of view about that? Okay. Let's talk about protons. They're found in the nucleus, have a positive charge. The number of protons determines the type of atom that it is. And the number of protons is the atomic number. So here in the case of cobalt, number 27, that tells you that a cobalt atom has in its nucleus 27 protons. So the atomic number for carbon is 6, oxygen is 8, hydrogen is 1. Now in a balanced atom, that means an electrically neutral atom, the number of protons equals the number of electrons, and that's approximately equal to the number of neutrons. The number of neutrons can vary, but protons always equals electrons if it's electrically neutral. So let's think about neutrons. They don't have an electrical charge at all. They're also found in the nucleus. The number of protons plus the number of neutrons gives the element its mass or atomic weight. And here you see in the periodic table, the atomic weight of cobalt is 58.9, rounded off to 59. Now electrons are so small that they do not significantly contribute to atomic weight, but we can figure out the number of neutrons by taking the mass weight minus the number of protons, and that will equal the number of neutrons. In the case of cobalt, the atomic weight is 59. The number of protons you see here in the corner, the atomic number, that's 27. The difference between them is 32. That's the number of neutrons that cobalt has in its nucleus. Forget that for now. And now electrons. The number of electrons is the number of protons in a neutral atom. It's always equal if it's neutral. The electrons orbit around, and not in the nucleus, they orbit around the nucleus. And they're in these orbitals or shells at specific distances from the nucleus. And that brings up what is an isotope. An isotope has the same number of protons and electrons, but it differs in the number of neutrons. And examples of that are carbon, phosphorus, and sulfur, all of which have isotopes of the normal atom. Now, each orbital or shell has a maximum number of electrons that it can hold at any one time. The first shell of any atom, doesn't matter which atom it is, the first shell can always hold maximum of 2. These electrons have a specific amount of energy. The second orbital can hold a maximum of 8. Now, these are a bit more energetic. And the most stable condition of for an atom is when its outermost shell is full. So we have the first shell with 2, second shell with 8. And the outermost electrons are called valence electrons because they're the ones that are exposed to the outside, to the world. And their number and position are largely determining the chemical behavior of an atom. So an atom with its outermost shell full is stable and unreactive, but atoms which do not have a full outer shell are reactive and can be very reactive. And here are some examples on the right. In the case of hydrogen, carbon, and sodium, in all cases, the outer shell is not full. In the case of hydrogen, it's a very simple structure. It has one proton and one electron. That means that hydrogen is very unstable, very reactive. Carbon similarly has 2 electrons in its inner shell and 4 in its outer shell. So it's missing 4, and it is very reactive. Sodium has 8 electrons in its second shell, but only 1 in the next shell, when it could have a maximum of 8 in its second shell. So sodium is a very reactive atom. In contrast to helium, which has 2 electrons, that's all it needs, so it's inert. Neon has 8, it's inert. And even though argon is a large atom, it's got a 3rd orbital, it has 8 electrons in it. So it is stable. All 3 of these are inert gases, and that's why you blow up balloons with helium and not hydrogen. Helium is safe, hydrogen isn't. So atoms.
Professor, I have a quick questions.
Yeah.
What is the difference between unreactive and very reactive?
Difference between reactive and unreactive is the number of electrons in the outer shell. So if the shell is full, remember the definition of full is the innermost orbital is full if it has 2. The second orbital is full if it has 8. And the third orbital is full if it has 8. Now, if the orbital is full, it's unreactive, it's inert. So all of these gases, argon, neon, and helium, have their outermost shell full of electrons. They don't want any more, they don't want to get rid of any, they're stable. Anything other than that, so hydrogen, in contrast to helium, hydrogen only has 1 electron, so it's very reactive. It either wants to get rid of this electron or share it or acquire another one. Carbon similarly, it would like to have 8 electrons in its outer shell, but it only has 4. So it's very reactive, either looking to get rid of its 4 or gain 4. Atoms are always trying to acquire a stable outer shell. Does that answer your question? The difference between reactive?
Yes, thank you.
And unreactive. Okay. Well, here we are back with Chan, carbon, hydrogen, nitrogen, and oxygen. These are the main elements in living things. And they're all very reactive. And why is that? Well, because you start with hydrogen, it's only got 1 electron in its outer shell, it would like 2. Carbon has 4 electrons in its outer shell, it would like 8. Nitrogen has 5, and it would like 3 more to make 8. And oxygen has 6, it would like 2 more to make 8. So these are the main elements that make up matter, make up living matter. And each of them is unstable because it's looking to complete its outer shell complement of electrons. And why am I going into all this? It's because this is how bonds form. That's what we're going to talk about next, is bonds. Bonds. Atoms with unfilled outer shells can become more stable by either acquiring electrons or sharing electrons. Now, for the moment, we're going to consider just 3 types of bonds. And I want you to remember these. They're all very important in biology. And I've put in red here, red letters, the the main thing about each of these types of bond. So an ionic bond forms when there are opposite charges. So this is an electrical bond. They're opposite charges, they attract each other, that forms the bond. A covalent bond, remember the word share. If it's covalent, it's because electrons are being shared between atoms. If it's a hydrogen bond, it's an electrostatic attraction. And we'll talk a lot more about hydrogen bonds because they are so critical for the construction of living things. Now what you see shown here is a covalent bond. What's the characteristic of a covalent bond?
They share
They share
electrons.
They share, right. And you see that you have two hydrogen atoms, they each have one electron. They come together, they share their two electrons. So now they both have two, and this is a stable hydrogen molecule. Now, what are ionic bonds? Ionic bonds are electrical attraction. So if there is an atom that transfers one of its electrons to another atom, two things happen. One is the atom that transfers an electron becomes positive in charge. Why does it become positive? Because it's lost a negative. Now the atom that receives that electron, which is negatively charged, becomes negative. It's just gained a negative charge. So now instead of having two atoms, we have two ions, one positive, one negative, opposites attract, and they form a bond, which is called an ionic bond. It's a relatively strong bond. And these type of bonds, an ionic bond is most common when an atom's outermost orbital contains just one or two electrons, or it needs just one or two electrons. And I'll show you how that happens with salt. Sodium chloride is made up of sodium atoms and chlorine atoms. Now remember that sodium in its outermost shell has just one electron. So it's very unstable. Chlorine in its outermost shell has 7 electrons, which it doesn't like. It would like to have one more to make 8. So sodium gives up its 1 electron. And when it does that, what happens?
Makes an iconic bond. Ionic, not iconic.
Yeah,
Well-
you said it. It becomes an ion with a positive charge, because this electron is negative. If it goes away, this atom becomes a positively charged ion. And now the electron goes over here to this chlorine atom, and now it's gained a negative charge. So it is now a,
Positive charged.
what's your name?
Justin Hansen.
Justin, okay. I have to record your names in order to give you credit for participating. Yeah, it's become a negative ion. Now plus and minus attract each other. And so that is the bond, the attraction between the positive ion and the negative ion of these two atoms. And this shows the same thing, except I've labeled them now. The positive ion, sodium plus, is called a cation. The negative ion, chlorine minus, is called an anion. So this is a crystal of salt. What you can see is that the chlorine atoms and sodium atoms are all clustered together. They're all attracted to each other by the ionic bonds between them. And we'll talk later about if you have a crystal of salt formed by ionic bonds, how does that go about dissolving in water? Now let's switch to covalent bonds, and you remember the key word here is share. Covalent bonds involve two atoms that share electrons. And you can see that illustrated. Again, we showed it before, but hydrogen atom has one electron, it's unstable. Another one has one electron, it's unstable. They come together and share their two electrons. Now they're both happy. I mean, they make a molecule. They go from two atoms to a molecule. And how do you represent a bond? Well, in the case of hydrogen, you can, the symbol for hydrogen is H. You can say H2, H subscript 2 indicates two atoms of hydrogen, or you can represent it as a bond, H bar H. This bar means that there is a single covalent bond between the two atoms. The number of single covalent bonds that it can form is equal to the number of additional electrons needed to fill its outer shell. So you can see in this case, there are two atoms here, each with 6. They each want to gain 2, so they each share 2 and make a stable molecule. And that molecule is oxygen, O2. 2 oxygens, or O double bar O. These 2 bars mean that it's a double covalent bond. That is, there are 2 electrons shared with 2 electrons. So that here I'm just comparing a double covalent bond with a triple. We've already seen this with oxygen. Oxygen, two molecule or 2 atoms, each share 2. So you get this configuration and you represent that as O double bond O. In the case of nitrogen, there are 3 electrons looking for partners. When they are shared, you get this configuration. And this is represented by N triple bar N. So remember that you'll be dealing when you do the worksheet with some of these conventions.
Professor?
Yeah.
Patrick Dowell here.
Okay.
Just curious question. Is that the highest it goes, is 3?
It's as high as I know.
Okay.
I can't say that, somewhere in chemistry, there's 4 or more. But I think in biology, 3 is as high as I've ever seen.
Okay, thank you.
Professor, I have a question. Sorry. Kiyomi Anderson. So when they're on the periodic table, would it have like the atoms by themselves and the covalent bonds?
No, the periodic table doesn't show bonding. It just
Okay.
shows the characteristics of a particular element.
Okay.
Okay, examples of covalent bonds and how you represent them. Hydrogen, we just said, is H bond H, single bond. Oxygen is a double bond, 2 lines. Methane, carbon is associated with 4 hydrogen atoms, each sharing its electron with carbon, so that now each of these 4 has 2 electrons in its outer shell, which is stable, that's what it wants. And carbon has 8, that's what it wants. And so it's represented by this configuration, C with 4 H's, each represented with a single bond. And similarly, water, O bond H, bond H. Carbon is the common denominator for biological molecules. Most, safe to say, all biomolecules have carbon as the basis. Why is that? Anyone have an idea?
My name's Katrina Bibbard. I was thinking possibly because the carbon has like an easy number to fill in because it has half of the shell filled, so it needs half more to be reactive, or it is reactive. That's why it can be.
Yeah, you're on the right track. It's reactive because it has 4 electrons in its outer shell, and it would like 4 more. So it can either give up 4, it can gain 4, or it can share 4. So it's very versatile in terms of forming bonds. And that's why life is a carbon-based entity, because carbon is so good at forming bonds with other molecules. And that's stated here in the second point, that carbon readily reacts because it needs 4 electrons to fill up its outer shell. Organic chemistry is the study of just materials that have carbon as their base, covalently bound to carbon. It has to be a covalent bond. Chemical formulas, in writing formulas, a number that has a number that's subscripted to the chemical symbol indicates that there are 2 or more of those. So O2 means that there are 2 oxygen atoms. CH4 means that there are 4 hydrogens associated with 1 carbon. H2O, 2 carbons with 1 oxygen. And C6H12O6 is a sugar, which has 6 carbons, 12 hydrogens, and 6 oxygens. And that's how they are written. In addition to indicating how many atoms are in each molecule, you can indicate the number of molecules. So if it's just CH4, that means it's 1 methane molecule. If it's 3 CH4, that means there's 3 methane molecules. Similarly, 12 H2O means 12 water molecules, and 7 of those is 7 sugar molecules. Polar and nonpolar covalent bonds.
Professor, could we go back to that last slide real quick?
Yeah.
Just to confirm for that very last one, the 7C6H12O6, is that saying that there are 7 carbon or 6 carbon there?
There are 7 sugar molecules.
Oh, okay. 7 of the, all right.
Go up to this part, you can see 1 sugar molecule is that. If you just put a 7 in front of it, then there are 7 of those molecules.
Okay, perfect. Thank you.
Okay, when electrons are shared equally between atoms, the molecule is nonpolar. So an example of that would be methane, where you have a carbon shares equally with 4 different hydrogen atoms. So the electrons are equally distributed through this molecule, and it's nonpolar. Similarly with oxygen. However, with water, H2O, the electrons are not equally distributed across the molecule. So this is actually wrong. This delta plus should be a delta minus. The oxygen is more electronegative than the hydrogen atoms, and so it attracts electrons to its side of the molecule, leaving the oxygen side a little bit negative and the hydrogen side a little bit positive. And that is a polar covalent bond, whereas a nonpolar one, electrons are equally distributed throughout. Polar covalent bonds. Now this is a reiteration of what I just said. Again, look at a water molecule. The big circle is oxygen. Two little circles are hydrogen. And oxygen is more electronegative than hydrogen is. And so it attracts this cloud of electrons is shifted more toward the oxygen side and away from the hydrogen side, so that the oxygen side is slightly negative, the hydrogen side is slightly positive. And this may seem sort of like small potatoes, but it really isn't, because it's the basis of hydrogen bonding. And among the electronegative atoms are oxygen, nitrogen, and chlorine.
Professor,
Yeah.
are those you mentioned delta? Are those little symbols? Those are the deltas down there?
Yeah, delta just means a differential.
Okay.
So it's a differential distribution of electrons. So if you think of these electrons as sort of like a cloud, the cloud tends to be shifted over the oxygen atom and away from the hydrogen atoms. Now this shows the same thing as in a slightly different form. Here on the right, you see a covalent bond. And again, this is with a water molecule. And what it's intended to show is this cloud of electrons is slightly shifted to the negative side, to the oxygen molecule. Again, I'm emphasizing this point because it is such an important one. This small, seemingly insignificant difference is really very significant. Electrons are shared unequally across this molecule. The electron density is greatest on the oxygen side and less dense on the hydrogen side, which leaves the molecule unbalanced, and therefore it's polar. So then the question comes up, what is a hydrogen bond? Well, it's defined as an electrostatic attraction between what and what? Well, it always involves a hydrogen atom and an electronegative atom of something else. So hydrogen bonds do not form between hydrogen atoms. It's always between a hydrogen atom and another electronegative atom, for example, oxygen or nitrogen. And because oxygen, nitrogen, and hydrogen atoms are abundant in biological systems, hydrogen bonds are very common. They're weak. They're weaker than covalent bonds, weaker than ionic bonds. They're easily formed and they're easily broken. And this is critical for life. For example, the DNA double helix could not possibly form without hydrogen bonds. Proteins would not be active enzymatically if they didn't fold properly according to the needs of hydrogen bonds. And for example, the specific heat of water is high because of hydrogen bonding. Without hydrogen bonding in water, it would boil at 80 degrees centigrade instead of 100 degrees centigrade, and oceans and lakes, all the water on the surface of the earth would evaporate. So we wouldn't have liquid water, we'd have gaseous water, which would escape into space. So life would not be possible if water didn't have hydrogen bonding. I show you this to represent how a hydrogen bond is usually represented as a row of dots. So what you see here are two water molecules hydrogen bonded to each other. So remember that a water molecule is electronegative on the oxygen side, electropositive on the hydrogen side. And so this electropositive hydrogen atom has an attraction to the electronegative side of the next water molecule. So that dotted line represents the attraction that this plus has for this minus. And that is a hydrogen bond.
Professor Taylor,
Uh-huh.
so even when they come together and they're bonded, would a hydrogen atom still, or hydrogen molecule still be unstable?
No, it's not stable. I mean, it's not unstable, sorry. It's not unstable anymore when they come together.
So when the bond forms, it stables out.
Yes. It stabilizes it, but it's a two-way reaction. It's an equilibrium. And I'll show you this when we talk about the different forms of water. Different forms, liquid water is an equilibrium of bonded and unbonded molecules. I'll show you that in just a minute. And this shows you that if you have multiple water molecules involved, it's always a hydrogen facing an oxygen. Here hydrogen faces that oxygen, this hydrogen faces that oxygen, hydrogen, oxygen, hydrogen, oxygen. So you have here 5 water molecules and 4 hydrogen bonds holding them together. And it can be very elaborate. You can have a lattice formed. Now, water is unique in terms of its chemical properties. And if it weren't for that, there'd be no life on this planet and maybe nowhere else either. So here are some of the interesting things about water. It's abundant on the Earth and it's found elsewhere in the universe. Its special properties are due to the fact that it hydrogen bonds, covers 75% of the Earth's surface. We are made of up to 95% water. It's the only substance on Earth found naturally in all 3 states of matter, solid, liquid, and gas. Any other substance is in 1 or 2 of these, but not all 3. It has a neutral pH, and I'll talk to you about pH in a few minutes if we have time. It's neither an acid nor a base. It's exactly in between. It's a universal solvent. It dissolves more substances than any other liquid, and it has a high specific heat, which I mentioned earlier. It can absorb a huge amount of heat without actually changing temperature. And that's critical for this planet because it's sitting in the sun. Some part of it is always in the sun. The sun generates a lot of heat. If it weren't for water acting as a thermostat, the Earth would alternate between extremely cold and extremely hot. Whichever side was facing the sun would be extremely hot. The other side would be extremely cold. But because water can absorb so much heat without changing temperature, the surface of the Earth is relatively constant. These are the different forms of water, and I want you to remember this because it's really very important. Solid, liquid, and gas water. So here on the left, you have ice. You see that every water molecule is bonded to every other, or bonded to another water molecule. All the water, the water molecules in ice are hydrogen bonded. So that's solid and it's stable. Liquid water is an equilibrium between bonded and non-bonded water molecules. So some of them, like here's a free one, here's another free one. Others are joined to one or more. But water is in constant motion, alternating back and forth between bonded and non-bonded water molecules. So given that, what would you say that what would you say that gaseous water is?
All separated?
Say it again.
All separated molecules?
Yeah, no hydrogen bonds.
Are they like, would they be like moving more than water or ice would be? Like, would they be like,
Yeah,
gyrating, wiggling?
right. They're very active, bouncing around as completely free molecules. So steam is water molecules that are not connected to each other at all. Gas, all hydrogen bonds are broken. So remember that. Yeah, go ahead.
Is there some kind of like connection though, like pulling them in? Because like you would think when steam is first made, like it doesn't just immediately disappear. It kind of lingers. You see the steam. Is it kind of like still held together a little bit, or?
I think not. I think once it's steam, there's no connection between any two water molecules, and it dissipates unless it undergoes these electronic attractions that occur that cause clouds to form. Clouds are very interesting in and of themselves. Why are there clouds instead of just dispersed water molecules? But that's a whole different topic.
Professor?
Yeah.
Keone Anderson. I had a question. So like if, happens to its hydrogen bonds? Because I understand they're broken, but like, where do they go?
Where do the bonds go?
Mm-hmm.
They're just not there. They never form.
Oh.
Anything else about water? Water is a very interesting subject. Properties of water: high specific heat. Solid phase is less dense than liquid phase. That's very important. There's a high heat of vaporization. It's a terrific solvent. And we have adhesion and cohesion properties. And I'll talk about each of these. I'm almost out of time, so I'll hurry along. On days that you have a quiz of 15 minutes, the class period is only 60 minutes. So I'll try to hurry. So specific heat means that raising the temperature of liquid water takes a large amount of heat input because the heat is used up to break the hydrogen bonds. So the temperature of the water remains roughly the same as the hydrogen bonds break. And if enough of them break, it becomes steam. So that means that, as I said earlier, the surface water on the Earth is like a giant thermostat, keeps the temperature relatively stable across the planet. And here's another very important characteristic, that because of hydrogen bonding, water is less dense as a solid than as a liquid. And if you think about that, any other substance that you know of is more dense as a solid than as a liquid. So the solid, put solid and liquid together, the solid sinks.
I have a question.
Uh-huh.
Is that why ice expands when it freezes, or water expands when it freezes? Because it's less dense?
I don't know why it expands when it freezes. Does anybody know?
I was just thinking that kind of makes sense, but yeah, I don't know.
Seems
Well-
like it would be related to that.
Yeah.
Yeah, I'm sure it's has something to do with it, but I don't know. That's a good thing to look up. Why water expands when all the water molecules are bonded. At any rate, water is unusual in that in its solid form, it floats on top of its liquid form. You see here this beaker. In the case of ice, the hydrogen bonds are stable. In the case of liquid water, the hydrogen bonds are constantly breaking and reforming. So at any point in time, there are free ones and there are bonded ones. Now, what's the consequence of that?
Professor,
Uh-huh.
so when we shake the bottle that contain the water in it, do we see like a oxygen bond?
When you shake a bottle of water,
Yeah.
I don't think shaking physical agitation would have anything to do with the hydrogen bonds.
So what do we do if we want to see the oxygen bonds in the water?
The hydrogen bonds,
Yeah.
the main factor that determines whether there are hydrogen bonds is temperature. So if you
Okay.
lower the temperature, they form. And if you raise the temperature, they break.
Okay. Thank you.
So it has a profound effect on life. This shows a mountain lake in the winter with ice on the lake surface. So the air temperature is very cold. It's below 0 degrees. The ice temperature is exactly 0 degrees, whereas the water temperature is higher than freezing. And as you go deeper in the lake, the deeper you go, the warmer the water. So the floating ice is an insulator between the air temperature and the water temperature. The deeper the lake, the warmer it gets. If ice sank, the oceans would fill up with ice, leaving no opportunity for aquatic life. If you think about that, ice forming from the bottom of the lake to the top, which any other substance would do, there'd be no life, at least in the winter, in lakes. Heat of vaporization, when you sweat, you lose heat. That's because of hydrogen bonding. And the important point I want to make on this slide is plants. Evaporation of water from the leaf surface helps keep plant leaves cool. Again, remember, plants are facing the sun all day, every day. They have to have a way to cool themselves. I'll talk about that in just a minute. But first, how does something dissolve? What happens when a substance dissolves? And we'll take the case of sodium chloride. So I'll just talk here about what you see in the diagram. Pour salt in water and it immediately starts to dissolve. Well, what's really happening? You see sodium ions are blue pluses, chloride ions are green minuses, water molecules are red and white. So you put a crystal of sodium chloride in water and immediately the water molecules start to hydrogen bond with the chlorine and sodium ions. So in the case of this sodium ion here, this blue one, you can see it has it's an ion, a plus ion. And so all the oxygen atoms are facing the plus ion because the oxygen atoms are negative positive attraction. Whereas if you look at a green chloride ion, the water molecules are the opposite. The hydrogen atoms are facing the chlorine and the oxygen atoms are pointing away. So these are all hydrogen bonds forming between hydrogen and electronegative atom. The electronegative atom can be either chloride or sodium. And so as more and more water molecules hydrogen bond to the salt atoms, it comes apart. And by the time you get to the bottom of this diagram, all of the sodium and all of the chlorine atoms are completely surrounded by water molecules, completely hydrogen bonded to water molecules. So if you ever wonder what's happening when, when a crystal dissolves, this is it. And finally, let's talk about plants and cohesion and adhesion. These are properties of water that allow plants to grow tall. So cohesion is the tendency of water molecules to stick to each other due to hydrogen bonding. Adhesion is the tendency of water molecules to stick to other surfaces due to hydrogen bonding. So how do plants get water? Well, through their roots. Take up roots into their tubes called xylem. And these end up in the leaves. The outer surfaces of the leaves have little openings called stomates. And water molecules are constantly leaving, going away from the plant through these little openings, going from liquid to gas as they leave. And because of cohesion, because these water molecules tend to stick to each other, the ones that have left as a gas are drawing up the liquid molecules. So the flow is from the leaf to the outside because of cohesion. Why does water move up in xylem vessels? Because of adhesion. That is the tendency of the water molecules to stick to the sides of the xylem tubes. So both of these forces draw water up in a plant, and that allows plants to defy gravity and grow away from it instead of just sprawling around on the ground. Surface tension. That's why a water strider doesn't sink, because of the surface tension of the water due to hydrogen bonds. And finally, excuse me, molecules can change shape because they can twist on their bonds. You see that here in this diagram. There's one configuration of this molecule, and if the molecule twists on its carbon-carbon bond, it can have a completely different shape. I'll skip over this for now. So I want to make a point about pH, if you have time to listen for it. pH is critical for life, and we run into different pHs many times in a day. And I just want to show you, I thought this was a nice diagram illustrating the range of pHs that we run into from 0, which would be hydrochloric acid, to 14, which would be sodium hydroxide. And if you look at biological systems, our stomachs have a pH of between 1 and 2. A lemon is very acid, as you know from biting into one. Apples and tomatoes are somewhat acid, banana less so. Water has a pH of 7. It is neither acid nor base. Blood is very close to neutral. And as you go on, broccoli, for example, is quite a basic food. And here you have bleach at pH 12 and sodium hydroxide, as I already mentioned. Drain cleaner is pH 13. Now, what do these numbers really mean? Well, I've got that here on the left. What is pH? Simply put, it's the hydrogen ion concentration. It ranges between 1 and 10 to the minus 14th gram equivalents of hydrogen per liter of water or of solute. The pH number is an exponent of 10. And these numbers range from 0 to 14. You see that here, 0 to 14. So if pH is an exponent of 10, then pH 0 is 10 to the 0, which is 1. 1 gram of hydrogen per liter, very acid. pH 14 is 10 to the minus 14 grams of hydrogen per liter, very low hydrogen ions, so it's basic. Does that make sense? You understand how pH numbers are derived at?
Taylor, so are you saying the lower you go on the table from 0 to 14, the less acidic it is?
Yeah.
Oh,
yeah. This scale is going from 1 to 10 to the minus 14th. So that's a really, really small number.
got it.
So that means that sodium hydroxide has almost no hydrogen ions in it. It has hydroxyl ions instead. So if you understand pH, you can understand how buffers work. In biology, a buffer is an organic substance that neutralizes hydrogen ions. It protects the pH of the solution from any major change. And in biology, when we're talking about characteristics of life, one of the characteristics is homeostasis. Well, part of homeostasis is a constant pH. So for example, in blood, you can't have blood changing in pH in reaction to something you eat. So blood is buffered. Most biological liquids are buffered so that they're always the same pH, regardless of what their surrounding environment is. Okay, yeah, that's the end. There's no other place in the course to talk about pH, and I wanted to get that in so that you would be familiar. When you see something about pH, or you think about eating a strawberry and it tastes acid, now you know why. So I'm going to stop and remind you that that the quiz, you still have till midnight to take the quiz. And if there are any quick questions before we go, be happy to deal with it. Otherwise,
Professor, I have a question. So basically, I still didn't get the idea of the attendance. So basically, every time when we come to the here, we have to tell our name. So you mark us present.
yeah, you can call your name, but what I'm really looking for is participation. So just now you spoke up, and so I've got to check by your name that you participated.
Yeah, because sometimes, like, I don't know, like the first class, I didn't mention my name because I didn't have any question or something. I think it was second or the first day. That's why I didn't get the idea.
Okay, well, you have it now. So
okay. So basically, I have to just mention my name so you mark me present, right?
yeah, that's the minimum. What I'd really like you to do is have a question or a comment about the topic.
Okay, sure. Thank you.
Professor
Owen, I have a question in regards to the quiz that's due tonight. Is it based on what we learned today or from previous classes as well?
It has nothing about today. It's previous week So it covers the structure of life,
Okay.
life in the universe, and classification of organisms.
Okay.
Those three topics.
And my name's Azar. Last name
Yeah.
Key, like Key.
Okay, I got you down.
Taylor,
Uh-huh.
so is this that one that you were talking about earlier, 15 minutes?
This is 15 minutes, yes.
All right, thank you.
Okay.
I
Yeah.
had a
Oh, you go first, Justin. Go ahead.
on the quiz, on the last question of the quiz, I like wrote extra stuff. I just could you like look at it or something? Because I don't want to like say what I wrote, obviously, but
Sure. I go over every question.
okay.
These quizzes and tests are always graded automatically by
Yeah.
called a speed grader, and it often makes mistakes. So I go through every question of every student and make sure it was graded properly.
Okay, cool. Thank you.
Professor?
Yeah.
This is not a question, just something interesting. I found a recent article. I just posted it in the chat. It reminded me when you were talking about in science, when you find a big discovery, it's not like, oh, I found that discovery. It's like, oh, seems odd. Just a really good example of that on Wired. They had a story about they found some life a couple miles underneath ice where they were not expecting to find any life, and it was pretty interesting.
Yeah, it was interesting. I read that article too.
You saw that?
Yeah, and
That's cool.
the big question was, okay, these things are alive, but there's no way that they can get food down there. There's no light. They're living in complete total darkness. They're
Right.
hundreds of miles away from any other living thing. So how are they getting food? And
Yeah.
they still don't know. It's coming from somewhere. Yeah, that was a fascinating article.
Is that the one that was on the polar ice caps?
On the what?
Polar ice caps that you were talking
Oh,
about?
yeah, that's under the Antarctic polar ice cap.
Yeah, I put a link in there, Taylor, if you want to check it out on the chat.
Yeah, I've already got it open. I'm already starting to read. Thank you. Man.
Okay, all right, good. Look, I will see you guys all on Monday.
Thank you.
Okay,
Thank
bye.
you.
Thank you. Have a good night.
Okay, take care, bye.